content on my face.
Yep. Yep.
Yes?
Yes, please. Yeah.
Okay, super. Thank you very much. I will just turn off my camera for connection purposes. So thank you again for this very warm welcoming. Again, it's great to be somehow back to Montsouris, although it's online. So thank you very much for organizing this cooperation between the Montsouris Center and the Remote Sensing Center of North Africa. I think it's a great opportunity to exchange a little bit from our perspectives. And today's objective is to talk indeed a little bit about the work I did in the region, but not only, I will extend it to some other longitudes towards the east. And I wanted to name this presentation From Plains to Mountains, Monitoring Water Challenges in the so-called Western and Central Asia through remote sensing. And so you have already heard about my background, thanks to Haleb. So indeed, yes, I did my bachelor and master programs in Lebanon. I was also working with the Green Plan at that time, and we were looking at agricultural terraces and mapping for hill lakes potential areas in Mount Lebanon. Then indeed, I did my PhD where I compared two agricultural plains, one in Lebanon, Bekaa, and another one in Iran, Marajdash, next to Persepolis. And there I looked at the contribution of remote sensing to the estimation of evapotranspiration and water challenges. But I will go more in details in a few slides. And after this, in 2020, I became postdoc at the University of Central Asia in Tajikistan. And from there, I continued my research on agriculture, but in different contexts. I also became the associate director for some times of the small research team that I'm working at here. But now I'm a senior research fellow, and I'm really looking at natural hazards and climate change impacts on agricultural sector, but also energy as well, mostly in Tajikistan, Afghanistan, and Kyrgyzstan. But I think these experiences are also relevant to Lebanon. So the questions that I try to raise during this little background is what are, the drivers from an economic and environmental perspective for agricultural strategies when we talk about arid areas? How do we cope with arid areas, resources, but also economic challenges? So I will try to answer these questions during this presentation. Of course, how remote sensing can support the estimation of crop evapotranspiration, but not only, many other things. This is at the core of my research, at least in the Western Central Asia. And from there, I also use remote sensing and other techniques to look at the sources of water, where the water comes from, the water that the farmers are using down the valley in Bekaa or many other places. Do we have changes over time with the sources and perhaps pretty. And there is another type of questions that I try to raise also is the impact of hazards on agriculture in high mountains. It's often an overlooked aspect of things of agriculture, but it's actually quite important in the region, as you would see. So as you understand, the tools that I'm using are remote sensing, a bit of things, and modelizations. So the presentation is divided like that in two parts. First, the plain, crop choices and adaptation to economic and climate drivers. So I really wanted to start this presentation with what we do with the water in terms of agriculture down the catchment before going up. So I had the chance to work in three different countries, such as Lebanon, Iran, and Afghanistan more recently, before 2021. And there I could look at the crop choices of farmers. So I conducted crop mapping using Sentinel-2 imageries of three representative plains of the countries to try to understand what people cultivate with figures, but also I went on the grounds to ask the farmers, why do you cultivate this instead of something else? In the case of Iran, we cultivate wheat and rice. That's very clear. In Bekaa, it's wheat and potatoes mostly. And in Afghanistan, it's north east part of Afghanistan. wheat and potatoes, and the three plains are in arid contexts. So the crop choices reasons are really good indicators about socioeconomic and environmental pressures on the farms, but also the crop choices themselves represent a pressure on the water resources as well. So when you talk to the farmers in these three plains of this wide region, most of them tell you that we cultivate, I don't know, wheat, potatoes, or rice because it's profitable, and this comes first. Only in Afghanistan I had answers such as we cultivate these potatoes only for self-sufficiency purposes. So that's another group of crop choices reasons. A third group was the lack of water. Well, in Iran, the farmers told us that we cultivate, for example, wheat and rice because we have a lack and shortage of water. That's one fact. We will analyze that a little bit later. In Lebanon, in Afghanistan, the lack of water is not as important in terms of reasons to cultivate this and that, but still it exists a little bit. So the question here was if this profitability and lack of water are really the main triggers and for cultivating this type of crops instead of others. And here we try to assess, the weight of the economy on strategies of agriculture with the weight of natural resources such as water. So to answer this question from a scientific perspective, I employed the well-known model Surface Energy Balance Model, PySebal at that time, which estimates the crop evapotranspirations, as you know well in the region, per crop type. So I could do this job only in Lebanon and Iran so far, but I'm planning to do it in Afghanistan as well. But it helps us to classify the crops per water demands, because from ETC, you can calculate the net irrigation requirements for each crop types. We have, for example, potatoes, which has a net irrigation requirement of around 400 millimeters per season. Rice, also in the case of Iran, 1,700 millimeters per season, so it's really big, and other values. So it's clear that these cultivations that are cultivated right now, such as rice or early and late potatoes in these two valleys, are actually mostly oriented towards the market and the profitability. And then the answer of the farmers which tell you like, look, we choose these crops because we have to adapt to the lack of water. Actually, it's not really solid reasons. The adaptation to market comes first. Because in the case of Iran, we have huge extent of rice cultivation, again, 1,700 millimeters per season. That's a lot for an arid area. And in Lebanon, it's not as strong as in Iran, but we have wine cultivation, as you know, of early and late potatoes, which combined together represents a big amount of net irrigation requirements. So all in all, when you calculate the water balances of the two plains, both are negative, at least on the year that I worked on. It was in 2017 and 18. In Marjdash, in Iran, for example, the farmers had to pump 0.25 cubic kilometers of water, while we only had 0.09 cubic kilometers of net precipitations, which could potentially recharge the groundwater that year. In Bekaa, the water balance is a bit better, where we had on that year 0.15 cubic kilometers of pumped water for irrigation, mostly potatoes, against 0.1 cubic kilometer of net precipitation. So these strategies, which are adapted to the market, again, because there is a market for rice and there is a big market for potatoes in the case of Lebanon, well, they lead to drawdown of the groundwater level. I asked the farmers uh, roughly what was the depth of their wells 30 or 40 years ago and the difference with today. And it's quite striking. In Marjdash in Iran, for example, we have a drop of 125 meters in 40 years because of this extended cultivation of rice on a wide scale. In Bekaa, again, it's a bit better, 40 meters, but still it's quite negative. And in Bamiyan in Afghanistan, we lost 13 meters over the last 3 decades. So it means that these agricultural strategies, again, have a high cost that we can quantify on the groundwater resources. But at the same time, when you combine remote sensing and interviews, you understand that farmers have no other choice than favoring crops which have high net irrigation requirements, such as rice or potatoes, but they are profitable again. And farmers in all the plains where I had the chance to work told me that farming is like gambling with different wordings, but that's the idea. We have no other choice than following the markets, even if we have to cultivate unsustainable crops, such as rice in Iran, for example. So what are the possible sustainable crops alternatives in the region? Well, we have four options, and by more sustainable, I mean cultivations which consumes less water than rice or early and late potatoes, for example. In Iran, we had few examples of some farmers cultivating canola and saffron, which have a much lower net irrigation requirement than rice. Well, that's pretty easy, but that would solve the problem for groundwater drawdown if we cultivated this in theory. In the case of Becca, we have the specific case of hashish and vineyards, and for both of them, I mean, all these alternative crops are calculated also the net irrigation requirements and has much less water demanding than early and late potatoes combined together. So the idea here was that if we cultivate all this type of cultivation, we could save some millions. Actually, a big surprise that we don't cultivate a lot of saffron in Marjdash or lots of vineyards in Bekaa because the market in this region is small for these specific crops, and the wholesalers are not interested by those. So again, the market and the wholesalers somehow have to dictate the sustainability of water resources in the region. But there are solutions such as canola and saffron or hashish and vineyards. So once we have this, this picture of what we do with the water in a sustainable, more or less sustainable way from the agricultural perspective, we have to ask ourselves, fine, that's what we do with the water, but where does the water come from? And do we have changes over time? Do we have less or more precipitation? And what are the consequences of these potential changes for agriculture? And this is where I propose you to travel a little bit further up in the mountains, or at least of Central Asia. And here I go to the second part of the presentation, which I entitled The Mountains Contributions of Different Water Bodies to Rivers and Stream. And here you have a beautiful view of Afghanistan from the Tajik side. Between myself and the landscape, you have the Amu Darya River, and you can really have the full picture here with the glaciers and the snow in the upper parts and the plots in the down the valley. So the main question that we ask first is, where does the water come from again in this region? Well, it's very important to highlight the role of snowmelts from Lebanon to Tajikistan in the end. It's been estimated that 30% of Mount Lebanon rivers are fed by snowmelt. That's quite important. In Zagros, which is in Iran, it's about 60%. Depends where, but mostly in the plains where I work, it's 60% of the discharge of the river coming from snowmelt. And even more striking, Amu Darya River, so in Central Asia, 65% comes from of the discharge comes from the snowmelt, and only 23% comes from rainfall, and only approximately 12% comes from the glacier ice melt. So it's a bit counterintuitive, but snowmelt plays a much more important role than glaciers in this region. The other interesting thing about snow, as you know, is that it's the most variable meteorological parameter, especially in high mountains. So there is a need. If the water comes from snowmelt, we must monitor it in a consistent way, especially in areas where we don't have data. And this is what we have proposed since the 2022 in Tajikistan, in the upper part of Amu Darya, where the snowmelt actually feeds the people. It's used for irrigation of potatoes, wheat, and vegetables in high mountains, but also snowmelt is used for energy production. because 100% in that part of the world of the electricity comes from hydroelectricity HPPs. So we must monitor the snow in that region. So every year during winter time, whenever we have a snowfall of more than 15 centimeters, we take our little car and we take many samples of SWE, snow water equivalents, to see the spatial distribution with in situ data over a small catchment quite representative of the area. Then with this in situ data, where we compare them with remote sensing estimation of SWE, such as FLDAS or ERA5 sometimes, and we compare a little bit to see their accuracy. But the nice things, as you know, with remote sensing and estimation, in that case of SWE, is that we can get the spatial and temporal distribution of SWE, and we can even look at potential trends over the last 25 years if we use FLDS. But I'm going to explain that a little bit better. So when you compare the SWE measurement that we take on an annual basis on the field with remote sensing such as FLDS on ERA5, well, it's not a big surprise, but remote sensing largely overestimates the SWE in this region of the world. So that's one fact. With RMSE of 107 millimeters between FLDS and in situ data. However, I should say that both products, ERA5 and especially FLDS, are good at showing the interannual variability of snow. When we have a low value of SWE in our in situ data over a year, FLDS will also show, compared to other years, relatively low values as well. So I would encourage to use FLDS in this part, and it also covers Lebanon, FLDAS, because it's good at giving the patterns from one year to another. And once we have this confirmation that the variability can be assessed by FLDS in an acceptable way, let's say, we can look at many metrics, and I will not go too much in details here, but in our catchments in the upper part of Tajikistan, when we look at the last 25 years trends, we can see a decreasing sweet peak and a shortening snow season in the east parts of Tajikistan. And what I say east parts, I mean the high plateaus that you can see on the photo on the top here. These are plateaus above 4,000 meters elevation, very dry already and very high. So there, the snow conditions are getting drier and the snow season is getting shorter, apparently already, despite variability. But to give you the complexity of the snow patterns in the region, in the west part of this catchment, we have the opposite trends where we have increasing sweep peak and increasing duration of snow seasons at the same time. And these are, like I said, in the west, and that's the second photo, where you have more complex orographic and topographic terrain with orographic effect, with lots of mountains and glaciers. And there, the conditions are getting wetter. So once you have these trends, we want to look at the potential effect of the drying or wetting wetter conditions in the catchments on the discharge. And we compare the correlation, we look at the correlation between the snow melt retrieved in FLDS with the discharge that we have in the city named Horog. Here, this is the outputs of the catchment. And all the areas in blue on the map shows you that, yes, we have a strong correlation between discharge and snow melt, so far so good. But there are other regions where the relation is much more complex. And indeed, when you look at the blue plots on the top here, this is the annual discharge of Horog since 2000. Kilometers per year of discharge, an average again. But when you look at the FLDS snow melts every year, we find 6, the output that we get. So it's another confirmation that FLDS largely overestimates the reality in the end. However, this big difference can be explained by different complex processes, because it's not because the snow melts that it reaches directly is lost in the glacier, because some glaciers store the snow melts through freeze and melt processes, Of course, the snow melt goes into the soil with infiltration, and then the drop of snow melt takes several years instead to reach the rivers. So that's why we don't observe it directly in the discharge. We also have a minor role of evapotranspiration in this area, 0.7 cubic kilometers per year. So the difference between the discharge and the snow melts in FLDS is not really much explained by evapotranspiration, but mostly by these long processes of infiltration and storage, because we also have lakes and reservoirs in the region which disturb the correlation in the end. However, again, another reason to encourage to use FLDS, the snowmelt retrieved in FLDS, whenever we have a year below average on the red plots in terms of snowmelts, well, it tells us that we are below average, so it's a relatively dry year during the whole period. During the same year, we can observe in the blue plot as well the same trend of discharge below or above average. So the dry years that we observe in SWE, in FLDS, sorry, in the red plots, we also observe them in the blue plots on the upper part. So these changes, of course, can have consequences, and I only talked about snow here. I'm not a glaciologist, but we should look at the glacial trends over time during the same periods. If you remove the contribution of glaciers to the runoff, and if you disturb the snow melt like we saw with the drying conditions in the eastern part, we can have a complete change of hydrological regime in the end. So the orange one here is a Niveau glacier regime, where we have the snow melts coming first, followed by during summertime a nice a peak from the ice melt. So that's the current situation. But if you remove the glacier from the equation with a drastic retreat, which is what we observe already, then we end up with a Niveau pluvial regime only, where you only have the peak of rain and snow at the beginning of spring, followed by nothing in the end. So it means that farmers would have to irrigate longer and from spring till the next precipitation. And this type of changes, which are the worst scenarios, have very significant consequences on the long term. This is again long-term projections here that I'm talking about. Another component of the water cycle in this region of Central Asia and underlooked, so we talked about glacier and snow, is the permafrost. So the permafrost, as you know, is the frozen soil in mountainous areas, and it's mostly known to be located in Siberia or north of Alaska. But we do have lots of permafrost in the mountains of Central Asia. It's been estimated that we have 24,000 square kilometers of it, according to some susceptibility maps here that you can see in purple. And why shall we look at the permafrost? In some region of the world, there have been also other studies saying that if the permafrost melts, the discharge of the river could increase by 19% in some cases, but in some cases, some other cases, 5%. So that's a big change. And the problem is that nobody knows how much water comes from the permafrost, although we have climate change trend, warming conditions, and it means that potentially the discharge of Amu Darya, for example, will also increase due to permafrost melt. But there is no data on this matter. So that's something we've been trying to investigate very recently with the University of Central Asia, where we track the water. So by tracking, I mean we use the stable isotope analysis, oxygen and deuterium. And this tells you where the water comes from, because each molecule of water have a very specific signature depending on its origin. And we can tell with this chemical chemistry if the drop of water came from permafrost or glacier or I don't know, rainfall or snowfall. And that's how we differentiate the contributors to the main discharge down there. So we just started this tracking system of permafrost. So we dig the soil in high mountains to find the permafrost or the so-called frozen soil. And then we do some isotopic analysis. It's a long shot study. And for this, we also have installed a very highly elevated weather station with some robots to measure the soil temperatures to see where the permafrost is located. Because if you have permafrost, you need to have temperature around zero in the soil. So that's what we do. And we have also installed the very first partial flume, as you can see on the photos here, of Central Asia at 4,800 meters elevation. It was tough, but it's worth it because it measures the discharge every hour now, and it tells us how much water comes from these small representative catchments where we believe there is permafrost. So this is, again, the beginning of this study, and we do already observe water coming from this catchment, although there is no more snow anymore, and we are at the end of summer on these photos, but still we have water coming from there. So it could be permafrost. And if we can quantify that, then we can roughly estimate if we have a significant amount of water coming from permafrost melt. And this could potentially be used as a next future source of irrigation in the long term. Of course, permafrost needs to be analyzed and monitored in the mountainous regions because beyond the discharge issue, when the permafrost melts, you have a very strong destabilization of the slopes, which triggers many frequent hazards such as gulf, landslides, and debris flows. So that's one thing, and it affects the agricultural lands because many of the arable lands are every year covered by debris. But more strikingly, and here I jump a little bit to another type of hazards, also related to snow avalanches, which has occupied a lot of my time the last few years. So why did I want to look at the snow avalanches? It's exactly the same story. Every year, some plots are covered by during spring by snow avalanches. So you have a partial destruction of the harvest every year. Amount of arable lands in the mountains, and if they are destroyed on a yearly basis by snow avalanches, then the food security itself is at threat just because of avalanches. So for this reason, I created a model on Google Engine, maps every year all the avalanches deposits that have happened on a regional scale. For this, I use Landsat archives. Why Landsat? Because now we have more than 300 statistics, more than with Sentinel-2 in terms of trends. So this tool is available. And quickly how it works, it's a very simple approach, but I wanted this approach to be efficient and simple so that everybody can use it. It maps using the NDSI the deposits that you see at the end of each winter, because only at the end of each winter you can make the difference on the images between the deposits and the surroundings with the bare lands once the snow cover has completely disappeared. And of course, depending on the elevation, you select different images, but we can talk about that later. So typical validation process, we compare the output of SAFE, snow avalanches frequency estimation, which we run in Google Engine and is automatically extracted. And we compare it with manually outlined deposits using high resolution imagery in Himalayas, but also in Switzerland, as you can see on the right. In blue on the right, you have the manually outlined deposits in 2018, outlined using Spot 6 images. And in red, you have the output of SAFE, which were automatically generated. So when I generate SAFE here, for example, I don't know where the avalanches are, but SAFE spots the areas where we have the remaining deposits at the end of every year, and I don't have to manually look at them one by one. So that's the strength of SAFE, which of course overestimates the surface and the number of avalanches, but still it can give you the patterns of where the avalanches are located. So here you have a small animation of how a SAFE output could look like. And from this, you can extract many things. You can tell where the avalanches occur most of the time, given the observations. And I did this work very recently on the buildings, the villages of Himalayas, the whole Himalayas, and we found out that 13% of the buildings in susceptible areas of avalanches in Himalayas are indeed approached, if not partially destroyed by snow avalanches every year. 13. For roads, it's 15%. 15% of the roads in Himalayas are at least once a year cut by snow deposit avalanches, which is a big problem for logistic reasons. And again, more interestingly, in my opinion, because it's overlooked, we calculated that 6% of Himalayas arable lands are covered by at least one deposit every year. So food security is definitely at threat, and we have this figure, 6%, just because of some avalanches on the plots. As you can see here on the round photo, for example, it's a very good illustration of that. And on the right, you have an example of how safe outputs can look like, where in red you have the high frequency of avalanches over the last 3 decades, and in yellow, the low frequency estimation. So it's really convenient tool for decision makers when they want to make mitigation measures, but it should be also used for agricultural purposes. Where shall we cultivate our plots given the patterns of snow avalanches? And this work also in Himalayas is under publication. So that's why you have this visual caption in here. But when you have 33 years of avalanches over a big region, you can tell whether there is more or less avalanches than in the past, or if nothing happened. So in the whole Himalayas, we calculated and we found that in SAFE that we had 60 million avalanches since the 90s. So it kind of makes sense because we have 35 years of study now. But the interesting part is that in 85% of the cases that I studied in Himalayas, no trends, which means that we don't have bigger or smaller snow avalanches deposits compared to the past. So there is not a strong and generalized impact of climate change on snow avalanches. And this is on the contrary of many other studies, actually, in that case. However, in 15% of the cases which I studied in the region, we indeed had an increase of avalanches activities, but it's only 15% of the basins that I studied in Himalayas. And there we see an increasing number of avalanches every year, wet avalanches in that case. And this is the interaction between meteorological triggers and avalanches occurrence is very complex because in only 6 basins of these 15% cases, we could explain literally by a multivariate correlation that indeed we have more avalanches because the SWE is increasing, wetter snow condition snowpack. The temperature is increasing in these parts as well, but we also have a replacement of rain, of snow by rain, because when you have rain on the snowpack, you have an increasing destabilization of the snowpack and a higher risk of avalanches. This could be only explained in the western part of Himalaya, sorry. These areas here in blue. So it covers Tajikistan, north of Pakistan, and east of Afghanistan, where only there we observe for now increasing activity of avalanches due to climate change, but only there. So it tells a lot about the complexity of snow parameters. So as a conclusion, you understood that I worked a lot with remote sensing and in different countries. And the key words of all of this, if we compile everything, is adaptation at 2 levels. Adaptation to environmental and socioeconomic viability, as we saw in Lubnan or around in Afghanistan. We have agricultural exposed to weather and economic viabilities, and farmers have to adapt to the volatility of the prices, but they also have to adapt to the lack of markets as well. But if you also include the mountainous agricultural sector, these people there also have to adapt their agricultural system to snow avalanches, which is an additional parameter which is threatening food security up there. And in some cases, as we have just seen in western of Himalayas, these activities of snow avalanches is increasing. So agriculture is definitely a threat for many reasons. So adapting to this is a challenge, to this variability is a challenge, but farmers have no other choice. And the idea of this work here is that we document this a little bit with some figures rather than assumptions. Another level of adaptation is long-term, as we saw in this presentation. Regime moving from glacial nival regime to only pluvial and nival regime. So that's a big change for a farmer, for changes in the snow equivalent trends, as we saw. And but there are still so many things that we don't understand. We don't know when precisely the big changes of farmers needs to be ready and informed about this. So that's why we need these scientific studies. That's why we also have to look at the permafrost, the role of permafrost, like I said, because for now it's a big unknown. We have all this ice volume beneath our feet up there, and we don't know how much is going to melt and what are the real consequences with figures from a discharge perspective. And when I say discharge, I mean agricultural and energy interests. So the regions where I've been working the last 5 years in Central Asia are very rich and interesting for sure, but there are lots of, I should say, uncertainties in terms of data. The data that we use sometimes, even from the stations, can be uh, overestimating the realities. We've seen some things like that. We also have a lack of weather station and monitoring in high elevation, but it's improving. It's been improving over the last 10 years, I should say. So the documentation of sources of water and impact of climate change is improving, but still we need more efforts. We need more remote sensing in this field and also more education stakeholders into that direction. Document this in order to inform for sure the government, but also the farmers through the government about the future potential changes, because some of them are quite rapid in the end. So I will stop here. Yeah, thank you for your attention, and yeah, I'm happy to hear any question here. Thank you.
Thank you, Arnold. So please, if you have any question, please write it in the chat. Meanwhile, I'll start by a question myself, Arnold, please. So when you mentioned the permafrost layer, so and you mentioned that you try to track its contribution to the discharge, but this won't be a renewable source, right? So if the source is being depleted, so its effect wouldn't last over time. Am I right?
Thank you, Ali. Yes, that's a very valid point. And maybe I didn't say it here, but when we present this work, we present it as a temporary source of water. Unless we have a continuous cycle of freeze and melt and sufficient precipitation in high mountains, which is still possible. But otherwise, yes, renewing permafrost takes thousands of years. So it's only a temporary resources, and beyond the disappearance of the active layer of permafrost, yes, that won't be considered as a renewable source of water. That's very, very good point.
I see.
Right.
I have another question, please, Arnold. So
Yes, yes.
when you mentioned that you weren't able to find a correlation between SWE and the discharge.
Yes.
So
Here.
Yeah, exactly. This slide, yes. So is this the case in other basins in other areas, or this was specific for your study?
It's specific for the study, actually. For now, we have only investigated this in this catchment, upper part of Amu Darya. So here you can see some areas of the catchment with strong correlations, right? In blue, for example. Maybe other catchments will have similar correlations, and some other catchments will have lower correlations. It's mostly due to the complex topographic terrain that you find in the red area, mountainous areas, steep slopes, lots of glaciers there, almost 1,000. And we believe that the presence of these mountains with glaciers disturb the correlation between discharge and SWE. Whereas in the blue areas, like you saw in the photography, we have a much more simple topographic feature with literally plateaus. And there, the correlation is more straightforward. So depending on what you have on your catchments, yeah, the correlation will move. But we only looked at this catchment for now.
Thank you. So, Dr. Farooq, please.
Thank you, Arno. Thank you for the presentation. And we had some gap in the voice during the presentation, but for me it was excellent. Yani. My question about, I don't understand how you extract the discharge from Cordex data, and you use it ERA 5 also?
So the discharge, I should have mentioned, is observed. You have the CT here, Horog, and this is the hydropost that I use. So it's data from, it's called Hydromet Agency of Tajikistan.
Okay.
Only the snow melt is remote sensing, yes.
Only snow melt.
Yes.
But what do you use it in ERA 5? Which parameter?
So ERA 5, we only looked at the correlation here, sorry, the error estimations. So it's in red on the plot here with the standard deviation. We only use ERA 5 till here, but then we found that FLDS was performing better compared to ERA 5 in retrieving SWE, only SWE. So that's why all of this, the trends and this work here with the correlation, is only FLDS. FLDS is 1 kilometer of resolution. It's daily data, and it was downscaled specifically for Central Asia. So that's why we wanted to look at it more particularly. Again, I think it covers Lebanon. So maybe you already use FLDS. It's a bit heavy to extract, but well, I can show to whoever wants one day how to extract it. But it's very, very useful. It's not good in absolute values like we saw, but it's good at giving, the patterns between a dry year and a wet year on the long term. So I would invite, remote sensing.
It is in the data catalog of Google Earth Engine, this data or not?
It's available data. I think I didn't catch your question, Aleb, but yes, it's available.
It's available, okay? In the data catalog of Google Earth Engine. Oh.
So this one is, there are two versions of FLDS. There is a global one with a coarse resolution.
We lost you for a minute, Arnold.
If you want specifics, so I probably missed some questions, so you feel free to email me if you have any specific questions.
Yes, I will send your email. We'll send your email to the participant, and I hope that we see you in Lebanon. Okay.
Inshallah, one day, yes, soon.
Okay. Thank you.
Thank you. Have a nice afternoon.
Thank you very much. Goodbye.
Bye.